November 24th, 1944. Nakajima Aircraft Plant, Musashino, Tokyo. Commander Takeo Shibata stood among the wreckage of what had been Japan's primary engine manufacturing facility just hours earlier. Twisted aluminum panels lay scattered across the factory floor, their American origins unmistakable. These fragments had once formed the wing and fuselage sections of Boeing B-29 Superfortress bombers, brought down by desperate Japanese fighter pilots and anti-aircraft crews during the morning raid. Shibata commanded the technical intelligence section of the Imperial Japanese Army Air Force, and his assignment was clear. Examine every piece of recovered B-29 wreckage and determine exactly what Japan faced. As he walked through the debris field, measuring fuel tank capacities and calculating wing loading factors, a terrible mathematics began taking shape. The numbers told a story that Japanese military planners had refused to accept. This bomber could reach Japan from bases 2,000 miles away, strike any target in the home islands, and return safely to airfields far beyond the range of Japanese fighters. Japan had no defense against what these aircraft represented. The strategic situation was not merely unfavorable, it was impossible. The first B-29 to fall on Japanese soil had crashed on November 1st, 1944, during a reconnaissance mission over Tokyo. The aircraft, belonging to the 3rd Photo Reconnaissance Squadron, had been damaged by anti-aircraft fire and fighter attacks before its crew bailed out over the city. Japanese recovery teams reached the crash site within hours, finding the aircraft surprisingly intact despite its violent impact. Within days, technical teams from multiple organizations converged on the wreckage site. The Kokugijutsu Kenkyujo, Japan's Air Technical Research Institute at Tachikawa, sent their most experienced engineers. The Navy's Technical Air Arsenal at Yokosuka dispatched specialists in aircraft structures and propulsion systems. Nakajima and Mitsubishi, Japan's primary aircraft manufacturers, contributed design engineers who had worked on Japan's own 4-engine bomber projects. All arrived with the same urgent questions. What made this aircraft capable of reaching Japan from distant bases? How did American industry produce such complex machines in meaningful quantities? And most critically, what could Japan do to counter this threat? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The B-29 represented a quantum leap beyond any bomber that had operated over Japan previously. Commander Shibata had examined captured American aircraft before, including several B-17 flying fortresses that had fallen into Japanese hands early in the war. Those examinations had revealed impressive manufacturing techniques and sophisticated systems integration, but the B-17 had been designed in the mid-1930s. Its basic architecture reflected pre-war thinking about strategic bombing. The B-29 was something entirely different. Every system appeared designed specifically to solve problems that had plagued high-altitude, long-range bombing operations. The pressurized cabin sections allowed crews to operate at altitudes exceeding 30,000 feet without oxygen masks or heated suits. The remote-controlled defensive gun turrets eliminated the need for multiple gunners exposed to freezing temperatures at altitude. The massive Wright R3350 engines, each producing 2,200 horsepower, drove the aircraft through the thin air at altitudes where Japanese fighters struggled to climb. But it was the fuel capacity that truly shocked Japanese engineers when they began their calculations. The initial examination took place in a commandeered warehouse near the crash site. Engineers carefully catalogued every piece of wreckage, photographing components from multiple angles and measuring dimensions with precision instruments. The wings, though badly damaged in the crash, retained enough structure to reveal their internal configuration. Japanese engineers counted fuel tank locations throughout the wing, measuring internal volumes and calculating total capacity. The numbers seemed impossible at first. Main tanks in the wings held thousands of gallons. Auxiliary tanks in the fuselage added still more capacity. As engineers compiled their measurements and consulted captured technical documentation, the total emerged. nearly 9,000 gallons of fuel capacity in standard configuration. Lieutenant Hiroshi Nakamura, an aeronautical engineer from Nakajima who specialized in fuel system design, performed the range calculations. He knew the Wright R-3350 engines consumed approximately 200 gallons per hour at cruise power settings. 4 engines meant total consumption of 800 gallons per hour. With 9,000 gallons aboard, the B-29 could remain airborne for over 11 hours. At a cruise speed of approximately 220 miles per hour, 11 hours of flight time translated to a combat radius exceeding 1,000 miles, allowing for climb to altitude, navigation to target, bomb run, and return with fuel reserves. But the implications went further. If the B-29 carried reduced bomb loads to accommodate additional fuel in bomb bay tanks, its range could extend to 16 hours or more of flight time. This meant a combat radius approaching 2,000 miles from base to target and return. Nakamura checked his calculations repeatedly, hoping to find an error that would reduce these devastating figures. The mathematics remained consistent. The B-29 could reach Japan from bases in the Mariana Islands, over 1,500 miles south, strike any target in the home islands, and return safely. Japan possessed no bomber capable of even half this range. Japanese fighters lacked the fuel capacity to intercept B-29 formations over the ocean and return to their bases. The strategic implications were catastrophic, and every engineer examining the wreckage understood them immediately. Lieutenant Commander Horikoshi Jiro arrived at the examination site 3 days after the crash. Horikoshi had designed the Mitsubishi A6M0 fighter, Japan's most successful aircraft, and his reputation as Japan's premier aeronautical engineer gave his assessments enormous weight within military circles. He spent hours examining the B-29's wing structure, paying particular attention to the fuel tank arrangements and structural design that made such enormous fuel loads possible. The Zero had achieved its remarkable range through extreme weight reduction, sacrificing armor protection and structural strength to minimize fuel consumption. Horikoshi had designed every component to serve multiple purposes, eliminating any unnecessary weight. The result was an aircraft that could fly immense distances but offered its pilot no protection and proved fragile under sustained combat stress. The B-29 represented the opposite design philosophy entirely. Its structure was robust, with heavy aluminum alloy sections forming a strong airframe designed to absorb combat damage and continue flying. The wings were thick, providing enormous internal volume for fuel tanks while maintaining structural integrity under load. The defensive armament alone weighed more than many complete Japanese fighters. Everything about the aircraft indicated that American designers had never considered weight reduction a primary constraint. They simply built stronger engines and larger airframes to carry whatever loads the mission required. Horikoshi recognized this approach as fundamentally different from Japanese design practice and far more effective for strategic bombing operations. A fragile, long-range aircraft like the Zero could be shot down easily if intercepted. A robust, long-range aircraft like the B-29 could absorb significant damage from fighters and anti-aircraft fire and still complete its mission. The examination expanded as more B-29 seconds fell over Japan in subsequent raids. Each crash provided additional data points, allowing Japanese engineers to confirm initial findings and discover new details about American capabilities. By late December 1944, technical teams had examined portions of 6 different B-29 seconds, documenting variations between aircraft and studying modifications that appeared in later production examples. The consistency of construction across multiple aircraft impressed Japanese engineers, just as captured B-17 seconds had revealed American mass production capabilities years earlier. Structural components showed identical dimensions across different aircraft. Panel forming matched precisely between multiple examples. Rivet patterns aligned exactly, indicating automated manufacturing using precision tooling rather than hand assembly. One B-29, that crashed relatively intact near Yokohama in early December, allowed detailed examination of internal systems. Engineers spent weeks cataloguing every component, measuring tolerances throughout the airframe, and studying manufacturing techniques visible in the construction. What they discovered confirmed the trend toward standardization and mass production that American aircraft had exhibited throughout the war. The electrical system used hundreds of standardized connectors throughout the aircraft. Any wire harness section could be replaced by removing a few screws and unplugging standardized connections. No soldering was required, no specialized tools beyond basic hand implements. The hydraulic system employed identical principles. Fittings used common thread standards throughout. Any hydraulic line or actuator could be replaced without modification or adjustment. Components were clearly designed for rapid field replacement by mechanics with basic training rather than specialized technicians. The engines themselves demonstrated American manufacturing sophistication that Japanese industry had never matched. The Wright R3000 350 duplex Cyclone consisted of 18 cylinders arranged in 2 rows, each cylinder precisely machined to tolerances measured in thousandths of an inch. Japanese engineers disassembled one damaged engine completely, measuring every component and documenting manufacturing techniques. The crankshaft alone represented a manufacturing achievement that Japanese industry struggled to replicate. Forged from a single piece of alloy steel, machined to precise dimensions, and heat-treated to specific hardness standards, the component would have required weeks of handwork in a Japanese aircraft engine factory. Evidence suggested American manufacturers produced these crankshafts using automated equipment at rates of dozens per day. Cylinder barrels showed identical internal dimensions across all 18 cylinders. Pistons were machined to tolerances that ensured perfect interchangeability. Connecting rods used identical bearing surfaces, requiring no hand fitting or adjustment. The entire engine was designed so that any component manufactured to specification would fit any engine without modification, allowing field mechanics to replace major assemblies using only basic tools and standard procedures. Captain Saburo Sakai, Japan's leading surviving fighter ace with over 60 confirmed victories, flew practice intercepts against a partially restored B-29 that Japanese engineers had assembled from parts salvaged from multiple crash sites. The reconstructed aircraft lacked engines and could not fly, but it was mounted on a truck bed and towed at high speed along a runway while fighters practiced attack approaches. Sakai had shot down numerous American bombers during his combat career, including B-17 seconds over the Pacific and various twin-engine types. He understood bomber defensive tactics and knew how to exploit weaknesses in their protection. The B-29 presented challenges unlike anything he had encountered previously. The remote-controlled gun turrets tracked attacking fighters with unnerving precision. The turrets could rotate faster than most fighters could maneuver, keeping guns pointed at threats throughout the attack approach. The fire control system linked multiple turrets together, allowing a single gunner to control several guns simultaneously and concentrate fire on priority targets. Most significantly, the turrets operated effectively at altitudes where Japanese fighters struggled to maintain control. Above 30,000 feet, where B-29 seconds routinely operated, Japanese fighters experienced severely reduced performance. The Zero fighter lost maneuverability at high altitude, becoming sluggish and difficult to control in thin air. The Ki-44 and Ki-84 fighters maintained better high-altitude performance, but still operated near their maximum ceiling when engaging B-29 seconds at their preferred altitude. Intercepting the B-29 required climbing to altitude, a process that consumed enormous amounts of fuel and left fighters with minimal endurance over the target area. If B-29 formations approached from over the ocean, Japanese fighters had to climb to interception, altitude over land, attack the bombers during their brief time over the target, then immediately return to base before fuel exhaustion. There was no possibility of pursuing damaged bombers out to sea or conducting extended combat over water. The B-29's range advantage extended to tactical situations, not just strategic deployment. Sakai submitted a detailed report to headquarters summarizing his conclusions from the practice intercepts. Effective attack requires closing to within 300 meters, despite defensive fire from multiple turrets, he wrote. Sustained fire for 3 to 5 seconds is necessary to ensure critical damage. Most attacks provide only 1 to 2 seconds of firing opportunity before breaking away to avoid collision or defensive fire. Multiple attack passes are required to achieve kills, but high-altitude interceptions provide only enough fuel for 2 to 3 passes before fighters must return to base. His report concluded with an assessment that matched what engineers had determined through their technical examinations. The B-29 can be shot down, but the resource cost of doing so exceeds Japan's capacity to sustain. For every B-29 destroyed, we expend fuel, ammunition, and pilot energy that cannot be replaced. American factories will produce replacement B-29 seconds faster than we can destroy them. The mathematics of attrition favor the enemy overwhelmingly. By January 1945, Japanese intelligence had accumulated enough information about B-29 operations to understand the full scope of the threat. The 20th Air Force, operating from bases in the Mariana Islands, had established a pattern of regular raids against Japanese industrial targets. Each raid involved hundreds of B-29 seconds flying in formation at altitudes where Japanese fighters struggled to intercept them effectively. The Marianas bases included Saipan, Tinian, and Guam, all captured by American forces in summer 1944 after bloody campaigns that cost thousands of Japanese lives. These islands sat approximately 1,500 miles south of Tokyo, well beyond the range of Japanese bombers but perfectly positioned for B-29 operations against the Japanese home islands. From these bases, B-29 seconds could reach any target in Japan, including the most distant factories in northern Hokkaido and the southern port cities of Kyushu. No location in Japan lay beyond their reach. More critically, Japan possessed no capacity to attack these bases directly. Japanese long-range bombers lacked the range to reach the Mariana Islands and return. Japanese naval aviation had been decimated in battles throughout 1944, losing most of its experienced pilots and many of its aircraft carriers. The combined fleet, battered by successive defeats at Philippine Sea and Leyte Gulf, could not project power 1,500 miles from Japanese home waters with sufficient strength to threaten American bases. Japan was strategically helpless, unable to prevent attacks on its industry while lacking any capability to strike back at the bases launching those attacks. Commander Shibata compiled his findings into a comprehensive report that circulated through Imperial General Headquarters in February 1945. The document, classified as most secret and distributed to only senior officers and key technical personnel, presented the conclusions that multiple examination teams had reached through 6 months of studying B-29 wreckage. The report began with technical specifications documented through examination of crashed aircraft. Wingspan of 141 feet, length of 99 feet, maximum takeoff weight exceeding 120,000 pounds, service ceiling of 33,000 feet, and most significantly, combat radius of 2,000 miles with standard fuel and bomb load. These specifications translated into operational capabilities that Japan could not counter. The B-29 can reach all targets within the Japanese home islands from bases in the Marianas. Our fighters cannot intercept effectively at the altitudes where B-29 seconds operate. When interceptions do occur, our success rate in shooting down B-29 seconds is approximately 3% per sortie, while each interception mission costs us fuel we cannot replace and risks pilots we cannot afford to lose. American production of B-29 seconds exceeds 100 aircraft per month, while our ability to destroy them averages fewer than 10 per month. The mathematical progression leads inevitably to the destruction of our industrial capacity. The report continued with analysis of manufacturing techniques observed in the wreckage. American aircraft construction demonstrates mass production capabilities that exceed our estimates by substantial margins. Component standardization is complete throughout the aircraft. Any part manufactured to specification will fit any aircraft of the same model. Field maintenance can be accomplished by mechanics with basic training using standardized replacement parts. This approach to manufacturing enables production rates that our industry cannot match. Most devastating were the strategic implications outlined in the report's final section. The B-29's range makes Japan's strategic situation untenable. We cannot defend against attacks we cannot prevent. We cannot attack the bases launching those attacks. We cannot replace industrial capacity destroyed in raids. We cannot intercept enough B-29 seconds to meaningfully reduce the bombing campaign. American industry will produce B-29 seconds faster than we can destroy them, and each raid reduces our capacity to resist subsequent raids. The strategic mathematics admit no solution favorable to Japan. Senior officers who read Shibata's report understood its implications, but few were willing to acknowledge them openly. Japan's military culture discouraged defeatist assessments, even when supported by objective evidence. Officers who suggested that victory was impossible risked being accused of undermining morale or lacking fighting spirit. The report circulated quietly through technical branches and intelligence sections, read carefully by engineers and analysts who understood its accuracy, then filed away without generating any policy changes or strategic reassessments. Meanwhile, B-29 raids continued with increasing intensity and devastating effectiveness. The March 9th to 10th firebombing of Tokyo killed over 100,000 people and destroyed 16 square miles of the city. Similar raids against Osaka, Nagoya, Kobe, and other industrial centers followed in subsequent weeks. Japanese industrial production collapsed as factories burned and workers fled to rural areas seeking safety. The B-29's range advantage made this destruction inevitable and unstoppable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical examination of B-29 Wreckage had revealed more than just specifications and performance characteristics. It had exposed fundamental differences in how America and Japan approached industrial warfare, differences that extended far beyond any single weapons system. Japan had entered the war with sophisticated engineering knowledge and highly skilled craftsmen capable of producing excellent individual aircraft. But Japanese industry lacked the systematic organization and automated manufacturing capacity to produce complex weapons at the scale modern warfare required. Each Japanese aircraft remained a semi-custom product, with components hand-fitted by skilled workers to match specific airframes. Quality varied between factories and between individual aircraft from the same factory. Parts from one aircraft rarely fit another without adjustment. Field maintenance required skilled technicians who could modify components to match the specific aircraft being repaired. This approach had worked adequately when producing thousands of aircraft, but it could not scale to produce the tens of thousands required for sustained combat against an industrially superior opponent. American industry, by contrast, had spent decades perfecting mass production techniques through civilian automobile and aircraft manufacturing. Precision tooling ensured that components met exact specifications. Automated assembly processes eliminated variability between products. Standardization meant that any part manufactured to specification would fit any product of the same model without modification. This systematic approach enabled production at scales Japanese industry could never match. Boeing's plant in Wichita, Kansas, produced B-29 seconds at peak rates exceeding 4 aircraft per day. Martin's plant in Omaha and Bell's plant in Georgia added additional production, bringing total B-29 output to over 300 aircraft per month by early 1945. These production rates reflected industrial capacity developed over decades of civilian manufacturing experience, capacity that could not be replicated quickly or created through wartime improvisation. Engineers examining B-29 Wreckage understood these industrial disparities through the physical evidence before them. The consistent quality across multiple aircraft demonstrated systematic manufacturing. The standardized components revealed design decisions that prioritized ease of production and maintenance over theoretical optimization. The robust construction showed that American designers never considered weight reduction a critical constraint, instead building whatever strength the mission required and accepting the need for larger engines and more fuel to carry the resulting weight. Every aspect of the B-29's design reflected confidence in American industrial capacity to provide whatever resources the design required. Japanese engineers had never enjoyed such confidence in their industrial base. They designed aircraft around severe resource constraints, minimizing weight to reduce engine power requirements, eliminating any feature not absolutely essential, accepting compromises in performance and capability to stay within manufacturing limitations. The Zero fighter exemplified this constrained design philosophy perfectly. By eliminating armor protection, reducing structural strength to minimum safe levels, and carefully optimizing every component, Horikoshi had created an aircraft with remarkable range and maneuverability within Japan's industrial capacity to produce. But the design had no growth potential. Any attempt to add armor or strengthen the structure would require larger engines that Japanese industry could not manufacture in sufficient quantities. Any modification to improve one characteristic degraded another due to the design's optimization around strict weight limits. The B-29 faced no such constraints. Its designers had built substantial margins into every system, providing growth potential for future modifications and improvements. If more armor was needed, the structure could support it. If heavier bombs were required, the bomb bay could accommodate them. If additional fuel was desired, the wings had volume for extra tanks. The aircraft could evolve to meet changing requirements without fundamental redesign because its designers had never accepted severe resource constraints as unchangeable limitations. Lieutenant Nakamura spent months analyzing fuel consumption data recovered from crashed B-29 seconds and comparing it against Japanese bomber designs. His findings documented disparities that went beyond simple range calculations. The B-29's Wright R-3350 engines achieved specific fuel consumption figures approximately 15% better than comparable Japanese engines at cruise power settings. This efficiency advantage came despite the Wright engines producing 2,200 horsepower per engine compared to 1,500 to 1,800 horsepower for the largest Japanese bomber engines. More powerful engines that consumed less fuel per horsepower represented manufacturing sophistication that Japanese engine makers had attempted to match but never achieved. The engineering knowledge existed within Japan. Japanese engineers understood thermodynamic principles and could calculate optimal cylinder dimensions, compression ratios, and valve timing. But translating knowledge into consistent production required manufacturing precision that Japanese factories could not maintain across thousands of engines. American engine factories produced crankshafts, connecting rods, cylinder barrels, and pistons using automated equipment that held tolerances measured in 10,000ths of an inch. Japanese factories relied more heavily on skilled machinists who produced similar components through handwork on conventional machine tools. The American approach ensured consistency across thousands of components. The Japanese approach produced individual components that might equal or exceed American quality, but with substantial variation between examples. This variation meant Japanese engines required hand assembly by skilled technicians who selected and fitted components to achieve proper clearances and balance. American engines could be assembled by less skilled workers following systematic procedures because precision was built into the components themselves. One approach could scale to enormous production volumes, the other could not, regardless of how many skilled workers were available. The fuel system examination revealed similar disparities. B-29 fuel tanks were self-sealing, lined with layers of rubber compounds that automatically sealed bullet and shell fragment holes to prevent fuel loss. Japanese engineers had attempted to develop similar self-sealing technology early in the war, but abandoned the effort due to rubber shortages and manufacturing difficulties. The B-29's fuel system included redundant pumps throughout, ensuring that engine feed continued even if some components failed. Japanese bombers typically used single pumps serving multiple tanks, creating vulnerabilities where single points of failure could disable entire aircraft. The B-29's approach was heavier and more complex, but dramatically increased survivability. American designers could afford the weight penalty because their engines provided ample power. Japanese designers could not because their engines provided barely adequate power for existing aircraft weights. By March 1945, the strategic situation had deteriorated beyond any hope of reversal. B-29 raids had destroyed much of Japan's remaining industrial capacity. The March 9th to 10th Tokyo raid marked a shift in American tactics from precision bombing of military targets to area incendiary attacks, designed to destroy entire urban districts, including the homes of workers who staffed factories. Subsequent raids against major cities followed similar patterns, dropping thousands of incendiary bombs that started firestorms across densely built residential areas. Japanese air defenses proved increasingly ineffective. Fighter units lacked fuel for adequate pilot training, forcing inexperienced pilots to face veteran American aircrews in technically superior aircraft. Anti-aircraft ammunition shortages limited the number of shells that could be fired at each raid. Many gun positions were abandoned as crews fled cities targeted by firebombing. The few successful interceptions that occurred cost Japan disproportionately. Destroying one B-29 typically required multiple fighters to attack repeatedly until accumulated damage forced the bomber down. Often several fighters were lost in the process, either shot down by defensive fire or expended through rams when ammunition ran out. The exchange rate favored America overwhelmingly. Each B-29 lost would be replaced by American factories within days, while Japanese fighters and pilots lost in combat could not be replaced at all, given fuel shortages and the near-total destruction of Japan's training infrastructure. This lesson influenced Cold War strategic thinking on both sides of the Iron Curtain. Soviet military planners emphasized building enormous production capacity for weapons systems, accepting that individual Soviet weapons might be less sophisticated than Western equivalents if Soviet industry could produce them in quantities that overwhelmed enemy defenses through numbers. American strategic planning emphasized technological superiority, but also maintained substantial production capacity as insurance against any conflict that evolved into extended industrial warfare. The B-29 also influenced thinking about strategic bombing doctrine and air power theory. The aircraft had proven that a bomber with sufficient range could strike any target within reach of its bases, regardless of enemy defenses, as long as the attacking nation could sustain losses and maintain production at levels that overwhelmed defensive capabilities. This capability fundamentally altered strategic calculations about defense and deterrence. Nations could no longer rely on geographic distance or local air defenses to protect critical industrial facilities from attack. Strategic bombers with intercontinental range made any target vulnerable regardless of location, forcing defensive planning to consider the entire national territory rather than just border regions or likely invasion routes. The development of nuclear weapons amplified this vulnerability by making a single bomber capable of destroying entire cities, but the vulnerability itself had been established by conventional strategic bombing campaigns that proved geography no longer provided protection against distant attackers. Japanese cities had been destroyed by conventional incendiary bombs delivered by aircraft operating from bases 1,500 miles away. The distance that once would have provided security instead became irrelevant when attackers possessed bombers with 2,000-mile combat radius. No amount of determination or tactical skill could overcome this strategic reality when the attacking nation maintained industrial capacity to sustain bombing operations indefinitely. By 1960, 15 years after Japan's surrender, the strategic lessons from B-29 operations had become case studies taught in military staff colleges worldwide. The U.S. Air Force Air University taught the bombing campaign against Japan as an example of how air power could achieve strategic objectives through sustained operations that destroyed enemy industrial capacity. The focus was not on individual bombing raids or tactical innovations, but on the cumulative effect of campaign, persistence enabled by long-range aircraft and overwhelming production capacity. Soviet military academies studied the same campaign from the defensive perspective, analyzing why Japanese defenses had failed to prevent the destruction of their industrial base. The conclusions emphasized the impossibility of defending against attackers with substantial range and production advantages, lessons that influenced Soviet development of surface-to-air missile systems, designed to create defensive coverage that fighter aircraft alone could not provide. Japanese defense planners, constrained by constitutional restrictions on offensive military capabilities, studied the B-29 campaign as illustration of vulnerability that geography could not mitigate. Japan's island nation status provided no protection against attackers with sufficient range to reach Japanese territory from distant bases. This vulnerability influenced Japanese security policy throughout the Cold War and beyond, making alliance with the United States essential for national defense, regardless of other political considerations. The technical documentation from wartime examination of B-29 wreckage remained classified in Japanese archives for decades after the war, finally becoming available to historians in the 1980s. Researchers studying these documents found detailed technical assessments that demonstrated Japanese engineering competence and realistic understanding of strategic situations, contradicting post-war narratives that portrayed Japanese military leadership as uniformly delusional about war prospects. The documents showed that accurate technical intelligence existed at working levels within Japanese military organizations. Engineers and technical officers understood American industrial capabilities and recognized Japan's strategic disadvantages. These assessments circulated through appropriate channels and reached decision-makers who had authority to act on the intelligence. But institutional culture and political constraints prevented this accurate intelligence from significantly influencing strategic decisions or forcing realistic assessments of Japan's prospects. Dr. Takashi Yoshida, a historian studying Japanese wartime aviation, published a comprehensive study in 1993 based on examination of the declassified technical reports. His work documented how Japanese engineers had systematically analyzed American aircraft throughout the war, accumulating detailed knowledge of American technical capabilities while watching their own strategic position deteriorate beyond any hope of recovery. The examination of B-29 wreckage represents a case study in how accurate technical intelligence can coexist with strategic delusion. Yoshida wrote, Japanese engineers correctly assessed American capabilities and accurately predicted the strategic implications. Their reports reached senior officers who had authority to influence policy. But institutional resistance to acknowledging unpleasant realities prevented this intelligence from generating meaningful policy responses. The result was that Japan continued fighting long after technical analysis indicated the strategic situation was hopeless, causing hundreds of thousands of additional casualties. Yoshida's work included interviews with surviving engineers who had participated in wartime technical assessments. These veterans, then in their 70s and 80s, recalled the frustration of documenting American advantages that everyone could see in crashed aircraft, but that few senior officers would acknowledge in strategic planning. We calculated that B-29 seconds could reach any target in Japan from the Marianas, recalled one engineer who had worked with Lieutenant Nakamura on fuel system analysis. We documented that American production exceeded our capacity to inflict meaningful attrition. We reported these findings through proper channels, but headquarters continued planning as though Japan could somehow achieve favorable outcomes through determination and fighting spirit, ignoring mathematics that admitted no solution favorable to Japan. Another veteran who had worked at Tachikawa examining crashed aircraft remembered the disconnect between technical reality and official optimism. Every crashed B-29 we examined proved Japan faced impossible strategic circumstances. The aircraft's capabilities exceeded anything we could produce. American industry could replace losses faster than we could inflict them. Geography no longer protected us because B-29 range made distance irrelevant. These conclusions were obvious to anyone examining the physical evidence, but stating them openly risked accusations of defeatism. The cultural factors that prevented realistic strategic assessment based on technical intelligence became subjects of extensive post-war analysis by Japanese historians and social scientists. The concept of fighting spirit, overcoming material, disadvantages had been so deeply embedded in military culture that officers who suggested material factors made victory impossible faced accusations of weak will or insufficient dedication. Institutional incentives all pointed toward optimistic assessments regardless of evidence, while pessimistic assessments, even when based on rigorous technical analysis, were discouraged or suppressed. These same cultural factors had influenced technical decisions throughout Japan's military development. The emphasis on achieving maximum performance specifications rather than robust reliability reflected cultural values that prized individual achievement over systematic organization. The acceptance of high maintenance requirements and specialized skills, rather than designing for ease of service, reflected cultural respect for craftsmanship over appreciation for systematization. American military culture, by contrast, had evolved through decades of integrating industrial production with military requirements. The U.S. Armed Forces had learned through experience that weapons systems must be producible in quantity, maintainable by ordinary soldiers and sailors, and robust enough to function under imperfect conditions. These requirements shaped American weapons development, forcing designers to prioritize characteristics that Japanese designers considered secondary. The B-29 embodied this American design philosophy completely. Its systems were robust rather than optimized, providing reliability margins that ensured function under field conditions rather than achieving theoretical maximum performance. Its components were standardized to enable mass production and easy maintenance, rather than being individually optimized for each application. Its structure was strong enough to absorb damage and continue flying rather than being lightened to minimum safe weight. Every design decision reflected lessons learned through decades of American military experience and industrial development. The resulting aircraft was not optimized for any single performance metric, but it excelled at the only metric that mattered strategically: sustained operational effectiveness over extended campaigns. It could be produced in enormous quantities by American industry. It could be maintained by mechanics with basic training. It could absorb battle damage and continue missions. And, most critically, it could reach any target in Japan from bases beyond the range of Japanese counterattack. The examination of B-29 Wreckage had revealed all these characteristics to Japanese engineers by early 1945, but by then, the strategic situation had deteriorated beyond any possibility of reversal. Japanese industry had been shattered by months of bombing. Fuel shortages prevented adequate training for new pilots or operation of what remained of Japan's air forces at meaningful sortie rates. Most experienced aircrew had been killed in action, leaving units staffed by inexperienced personnel flying against veteran American crews in technically superior aircraft. The March through July 1945 period saw Japanese cities systematically destroyed by firebombing raids that Japanese defenses could barely contest. Tokyo, Osaka, Nagoya, Kobe, Yokohama, and dozens of smaller cities burned in massive conflagrations that killed hundreds of thousands of civilians and left millions homeless. Industrial production collapsed as factories burned and workers fled to rural areas. Transportation networks were paralyzed by destruction of rail yards and port facilities. Each raid demonstrated the strategic helplessness that examination of B-29 Wreckage had predicted. The aircraft came from bases Japan could not reach, flying at altitudes where interception was difficult and rarely successful, delivering bomb loads that destroyed entire city districts, then returning safely to distant bases to prepare for the next mission. The campaign continued without pause despite occasional Japanese successes in shooting down individual bombers, proving that attrition could not reduce the campaign's effectiveness when American production replaced losses within days. The atomic bombings of Hiroshima on August 6th and Nagasaki on August 9th represented the culmination of strategic bombing capability that conventional B-29 raids had already demonstrated. A single bomber could now destroy an entire city with one bomb, eliminating any possibility that defensive measures might protect population centers or industrial facilities. The strategic helplessness that Japanese technical officers had recognized months earlier had become absolute. Emperor Hirohito's surrender decision on August 15th came after months of devastating conventional bombing had already made Japan's strategic position untenable. The atomic bombs accelerated the decision, but did not fundamentally change the strategic situation that B-29 operations had created. Japan faced an enemy who could destroy Japanese cities and industry at will from bases beyond Japanese reach, using production capacity that exceeded Japan's ability to inflict meaningful attrition. In the decades following the war, the B-29 became recognized as one of the most strategically significant weapons systems of World War II, not for any single dramatic action, but for its cumulative impact over months of sustained operations. The aircraft had proven that industrial capacity and long-range striking power could achieve strategic objectives that tactical victories could not accomplish. Nations with sufficient industrial depth to produce long-range bombers in quantity could project power over distances that made geography irrelevant as a defensive factor. These lessons influenced military planning throughout the Cold War. Strategic bombers remained central to American and Soviet military planning, despite the development of intercontinental ballistic missiles, because bombers provided flexibility and visibility that missiles lacked. The B-52 bomber, developed in the 1950s as the B-29's spiritual successor, continued in service into the 21st century, demonstrating the enduring value of long-range strike platforms. Japanese engineers who had examined B-29 wreckage during the war lived to see their nation become a close ally of the United States and a global industrial leader. Some found bitter irony in Japan's post-war success, achieved by applying the same systematic manufacturing principles they had observed in American weapons they could not counter. Others took satisfaction in contributing to Japan's transformation from defeated nation to economic powerhouse, using knowledge gained through wartime technical intelligence to rebuild their country's industrial base. Commander Shibata retired from the Japan Defense Agency in 1972 after a post-war career advising on technical intelligence and aviation development. In retirement, he occasionally lectured at universities on wartime technical assessments and their influence on post-war industrial development. His lectures included detailed descriptions of examining the first crashed B-29 inches, November 1944, and realizing within hours that Japan faced strategic circumstances that admitted no favorable outcome. The aircraft told its story through metal and machinery, Shibata would explain to students. We measured fuel tank capacities and calculated range. We examined engine construction and assessed manufacturing quality. We studied structural design and evaluated production methods. Every measurement confirmed that American industry had achieved capabilities Japan could not match. The strategic implications were clear to anyone who understood the technical evidence. He continued, the B-29's range made Japan defenseless. We could not prevent attacks on our cities. We could not strike the bases launching those attacks. We could not produce aircraft in numbers sufficient to inflict meaningful attrition. The mathematics admitted no solution favorable to Japan. We documented these conclusions and reported them through proper channels. But institutional culture prevented realistic strategic responses based on technical intelligence. The result was unnecessary continuation of a war that technical analysis indicated was already lost. Shibata died in 1988 at age 76, having witnessed Japan's transformation from devastated, defeated nation to prosperous, peaceful democracy and global industrial leader. His wartime technical reports, declassified and donated to Japanese archives, remain valuable primary sources for historians studying Japanese technical intelligence capabilities and the disconnect between accurate technical assessment and strategic decision-making. The B-29 itself became a museum artifact and historical curiosity, with surviving examples displayed at aviation museums in the United States and restored by enthusiasts who appreciated the aircraft's significance in aviation history. The Enola Gay, which dropped the atomic bomb on Hiroshima, became perhaps the most controversial museum artifact in American history when the Smithsonian Institution attempted to mount an exhibition. examining the aircraft's role in a broader context of the bombing campaign's effects. The controversy illustrated continuing sensitivity about weapons that had achieved strategic objectives through methods that killed hundreds of thousands of civilians. The B-29 firebombing campaign killed far more Japanese civilians than the atomic bombs, but conventional incendiary attacks generated less controversy than nuclear weapons, despite causing comparable or greater destruction in some cities. Tokyo's March 9th to 10th firebombing killed more people than either atomic bomb, but received less historical attention than the nuclear attacks. From the Japanese perspective, documented through examination of B-29 wreckage, during the war, the distinction between conventional and nuclear attacks was largely irrelevant strategically. Both demonstrated American capacity to destroy Japanese cities at will from bases beyond Japanese reach. Both proved that geography provided no protection against enemies with sufficient range and production capacity. Both showed that Japan's strategic situation was hopeless once the United States committed its industrial resources to strategic bombing campaigns. The technical intelligence gathered through examination of crashed aircraft had predicted this outcome months before Japan's surrender. Engineers measuring fuel tanks and calculating range had understood that Japan faced an enemy whose industrial capacity and long-range striking power made defensive victory impossible. Their assessments proved accurate, but came too late to influence strategic decisions that might have shortened the war or reduced casualties. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe